All right, let's go through another sample problem in section 2. Still working with vector operations. This time, we're going to be adding vectors algebraically. So, here is our prompt. A hiker walks 27.0 kilometers to her base camp at 35 degrees south of east. The next day, she walks 41.0 kilometers in a direction 65 degrees north of east and discovers a forest ranger's tower. Find the magnitude and direction of her resultant displacement. So, first thing we want to do, select our coordinate system, and we're going to sketch and label each vector. Okay, some things that we know. We know that our first resultant, 27.0 kilometers, and our second resultant was 41.0 kilometers. Now, what's really important about defining our coordinate systems is understanding that in order to numerically represent direction, we have to have sign conventions. And so you can see that the first theta, the first angle, is negative because clockwise movement from the positive x-axis is negative by convention. And we can represent that with a drawing, and we can see that traveling quote-unquote south of east, right, going down the y-axis, below the x-axis is negative by convention. But from that position, okay, she travels north of east, and north, okay, traveling on that positive y-axis is why the second theta is a positive value, 65 degrees. So here we are trying to figure out the overall resultant and the overall angle of displacement, which is represented on this this diagram with kind of that dotted line, right? We can actually use my mouse. This dotted line right here, okay, and you can see here is the overall resultant, d, that I'm trying to solve, and here is regular old theta, not theta 1 or theta 2, just theta. This is what I'm going to be solving for. So, in order to do this, we are going to have to make separate sketches for the displacements for each day. We can use the cosine and sine functions to find the x and y components of each resultant. Okay, so for the traveling on day 1, okay, so we'll call it, sub 1, we have the x component of that displacement, and we have the y component of that displacement, and we'll represent it as delta x sub 1 and delta y sub 1. And we have the very first resultant, which again was 27.0 kilometers. We're going to represent that as d1, right, displacement 1. And you can see here that we're going to use, for delta x1, we're going to use cosine theta 1. And you might be thinking, how do I know to use cosine? Well, remember your definition of cosine. Here's your theta. Okay, here's your angle. We're trying to solve for the x, right, delta x. That's this side right here. Now, relative to this angle, this is the adjacent side. It's the side adjacent to the angle. So when you go adjacent hypotenuse, that's the definition of cosine. Kind of conversely, for the delta y sub 1, right, which is this component, again, relative to the angle, the delta y1 is opposite. So you guys know that opposite over hypotenuse is sine. It's the definition of sine. So now that we have these representations, we can plug in the values, right? The displacement 1 for day 1 is the same for both situations, 27.0 kilometers. And we have the cosine of the angle and the sine of the angle for x and y components, respectively. But remember, we have to include this negative sign, the negative 35 degrees, right? Because that's how we represent the direction, meaning south of east, numerically. And if you do not include that negative sign, your numbers will not come out correctly. Well, we can set up the exact same situation for day 2, and I'll simply represent those with a subscript 2. Okay, so delta x2, delta y2, and I'll be using the second displacement, so d sub 2, and you'll notice that there's also theta sub 2. We're using the same definitions of cosine. That's why when trying to solve for the x component of the second displacement, again, relative to this angle right here, the x component is the adjacent side. So adjacent over hypotenuse is your cosine. For the y component, Again, relative to the angle, it's opposite over hypotenuse, which is the definition of sine. So again, I can plug in the displacement for day 2 and multiply that displacement by the cosine of 65 degrees for the x component of that displacement. Multiply that 41.0 kilometers by the sine of 65 degrees to figure out the y component of that displacement, which is 37 kilometers total. So now that we have two sets of x and y components, okay, so we have an x and y component for the first day and an x and y component for the second day, we can actually add them all back together. So we can take delta x1, add it to delta x2, which is 22 kilometers plus 17 kilometers for a total of 39 kilometers. And then we can do that for delta y, right? Delta y total is equal to delta y1 plus delta y2, which is negative 15 kilometers. That's why that negative sign on the 35 degrees was so important, plus 37 kilometers, for a total of 22 kilometers. Now that we've done that, we can actually draw a new triangle and use the Pythagorean theorem, right? And so, again, Pythagorean theorem, d squared is equal to x squared plus y squared. Solving that for d, we have to square root both of those. And so we've just created these x total, this x total and the y total, and so we can plug those values in for into the Pythagorean theorem. Some simple calculator work will tell me that this overall resultant is 45 kilometers. Well, lastly, we can use a suitable trigonometric function to find the angle, and it sounds like arctangent is a good way to do it, right? So to solve for the angle, we're going to take the arctangent, and again, based on the diagram that we've drawn, it's opposite over adjacent, so that means the y component was opposite and the x component was adjacent, so it's going to be delta y, which is 22 kilometers, over delta x, which is 39 kilometers. Making sure that you use the inverse tangent function, you should come up with 29 degrees north of east.